Good morning. Today I am going to explain matched filter. Matched filter. Matched filter. The concept of matched filter is, if you take a digital communication system, in digital communication system the information is in the form of 0 and 1. In digital communication system the information is in the form of 0 and 1. For example bit 1, if I take bit 1 for example I am represented like this one, 0 at a TB period, and I am assuming the voltage of bit 1 is 5 volts, and another one bit 0 I am representing here for TB period. Voltage of bit 0 is 0 voltage. Okay. Voltage of bit 0 is 0 voltage. Now this signal, if it is affected by the noise, the same signal will be look like this is 0 TB 5 volts. If it is affected by the noise, the signal will be like this one. Here also the bit 1 is also affected by the noise, so here it is also look like this one. Okay. Now see here, now I want to find the error, bit error. So here in this case, input signal, let us take input signal is my input signal is S of t. I am assuming my input signal, that is this is S of t signal, or this is S of t signal, right? This signal is added by some noise. This signal is affected by some noise N of t, and output of this signal, if the signal is affected by the noise, here we cannot take exact this voltage, so we have to take a sample value at particular in TB duration. We can take one anywhere, we can take the sample value. So that to take the sample value, so here I am taking sample at t is equal to TB duration, and here I am, there is a device that is threshold comparator. Threshold comparator. This threshold comparator, it consisting of a voltage level, that is V threshold voltage. Now let us assume, see here, this is my S of t signal, this is my S of t signal. I am assuming this S of t signal is a 5 volts for bit 1, 5 volts for bit 1, and it is added, this signal is added with noise. After noise, we can assume this voltage is 4.8 volts, right? At t is equal to TB, the voltage at this point is 4.8 volts. This 4.8 volts is compared with the threshold comparator with internal level of threshold voltage. The meaning of threshold voltage is the average voltage. Now if you see here, this is 0 to 5 volts. What is the average? Average is 2.5. So now comparing here, if the sample value is greater than 2.5, the threshold comparator, it produces output in the favor of bit 1. If the sample value is less than 2.5, the threshold comparator, it produces the output in the favor of bit 0. Now see here, this value is 4.8, so that this 4.8 is greater than 2.5, so that the threshold comparator will produce bit 1. So I am transmitting here bit 1, I received the same bit. Now if the noise is more, the noise is affected the input signal by more, so the signal is becomes, if noise is affected more, the signal, see here, this is 0 to TB and 5 volts, and it is affected by the noise is more, so that I am writing here the figure becomes this one, right? Now this is off part, this point I am written as 2 volts. If noise is more, now see here I am taking sample at this point, the sample value is 2 volts. The case 2, the sample value is 2 volts. Now at t is equal to TB, the sample value is 2 volts. This 2 volts is comparing with threshold voltage. So here sample is less than 2.5. So here instead of bit 1, I am getting bit 0. So I am transmitting bit 1 here. It is affected by the noise more, and I am receiving bit 0. This error is called as bit error. This error is called as bit error. Right? In order to overcome, we have to use filters. In order to overcome this bit errors, we have to use filters. So these filters, it is used to improve the signal to noise ratio. The filters are used to improve the signal to noise ratio, means when the signal power is more compared to noise power, so that we can reduce the bit error, right? So by using that concept, I am designing a filter, that filter named as matched filter. Okay. Now see here, I am going to design a filter, that filter named as matched filter. So here input signal S of t, and it added with the noise N of t, and output of this signal is passing through filter H of t. This is my filter, you can call it as matched filter. Then output of the filter is passing through a sampler at a t is equal to TB, okay, and output of this one is passing through threshold comparator. Threshold comparator with internal level is V threshold. Now see here, this is my new diagram. So just here I am inserted a filter to overcome bit error. Let us assume the output of my summer, I am call it as R of t. The output of filter I am representing here Y of t. The t is at t is equal to TB samples. The output here I am call it as Y TB, right? And here I am getting output. So here my aim is to improve the signal to noise ratio. By increasing the signal power, automatically we can reduce the bit errors in digital communication system, right? Let us take here the received signal R of t. The received signal R of t is equal to S of t plus N of t, right? And output of the filter Y of t is equal to R of t convolved with H of t, right? Now here I want to substitute R of t value. Y of t is equal to R of t is S of t plus noisy signal N of t is convolved with H of t, right? Now I want to separate this one. S of t is convolved with H of t plus this noisy signal is also convolved with H of t. Now here in this case, this is signal and it is belongs to noise component. Signal component I want to write this one. Signal component is YST and this is noise component is y and t, signal component and noise component, right. Now first of all I am going to find the noise component, right. I am going to find the noise power. So I did finding noise power, finding noise power, finding noise power, right. So in finding noise power we know that, right. So input signal is a noisy signal that is passing with filter h of t. I am getting here noise component that is yn of t, right. So this yn of t is n of t convolved with h of t. This is noise component. Now here whenever we are representing noise, so that should be a Gaussian noise, white Gaussian noise. Its power spectral density of the Gaussian noise is n0 by 2, right. So here I am going to find here power spectral density output, here power spectral density output is equal to, simple equation, power spectral density input, right, power spectral density input and modulus of filter square. This is the equation, right. Power spectral density output is equal to power spectral density input and with s this output filter modulus of filter in Fourier transform. Okay. Now see here, this is in time domain. So convolution in time domain, so it can be written as frequency domain is equal to n of f and h of f, right. Now see here noise power, here I am writing noise power. The noise power I am representing with NP, noise power is equal to, right, the simple equation, the noise power is equal to integral minus infinity to infinity power spectral density output df. The noise power is equal to power spectral density output is equal to into df, right. Now this can be written as noise power is equal to, right. Now what is the power spectral density output? Minus infinity to infinity power spectral density output is equal to power spectral density input. Power spectral density input is n0 by 2. So n0 by 2 into, right, into mod h of f whole square, right, mod h of f whole square into df. So finally here noise power is equal to n0 by 2, noise power n0 by 2 integral minus infinity to infinity h of f modulus whole square into df. Okay. This is noise power equation. Now similarly I am going to find the signal power. Signal power, signal component is s of t convolved with h of t, right. Now finding signal power, finding signal power, finding signal power. Finding signal power, right. So in finding signal power I said here input signal is s of t is passing through filter h of t, is passing through filter h of t, right, and the signal component that is y s of t is equal to s of t convolved with h of t. Okay. So this is also be written as y s of f, ys of f is equal to s of f into h of f. Is it right? Now see here, here we know this ys of f. Okay. Now inverse Fourier transform of ys of t, general inverse Fourier transform ys of t is integral minus infinity to infinity ys of f e power j 2 pi f t df, right? So this is inverse Fourier transform equation. Ys of t is equal to integral minus infinity to infinity ys of f e power j 2 pi f t df, right? We know the value of ys of f. This is, so here I want to write ys of t is equal to integral minus infinity to infinity s of f h of f, okay, e power j 2 pi f t df. Now this signal is passing through a filter, right? After filter it is passing through a sampler, right? See here, it is passing through sampler at t is equal to tb. So when y of t is passing through at sampler, we will get a DC signal, that is ytb. Okay. Now it is passing through sampler, passing through sampler, t is equal to tb. So ys tb is equal to integral minus infinity to infinity s of f h of f e power j 2 pi f tb df, right? Now here I am going to calculate power. So whenever passing through sampler t is equal to tb, so the signal becomes a DC signal, yes or no? See here, so this signal is passing through, here I am taking a sample value at t, this particular value in this duration. So after taking sample, this signal becomes what? This is a type of DC signal, right? The DC signal, the power of the DC signal is signal square. So signal power, that is, I am writing here signal power SP is equal to ys tb, signal power is equal to ys modulus ys tb whole square, right? By finding signal power, SP is equal to ys tb whole square means modulus integral minus infinity to infinity s of f h of f e power j 2 pi f tb df modulus square. Now here I want to calculate signal to noise power. This is my signal power. Now here I am going to calculate signal to noise power. Okay. Signal power by noise power is equal to, signal power is minus infinity to infinity s of f h of f e power j 2 pi f tb df whole square by noise power. What is the noise power? Just now we are calculated, that is n naught by 2 integral minus infinity to infinity, right, h of f whole square mod square to d of f. This is signal to noise ratio, right? If you see here, there is no chance to cancel any term. So here by using inequality, signals inequality equation, the inequality equation says that by using by using Schwarz inequality theorem or equation, the equation says that any signal, it is look like modulus f1 of t into f2 of t into dt modulus square, it can be represented as less than or equal to integral minus infinity to infinity f1 of t whole square dt into integral minus infinity to infinity f modulus f2 of t square dt, provided where f1 of t is equal to complex conjugate of f2 of t. This is called as Schwarz inequality. By using this one, I want to separate the signal component, right? The signal component is look like here. So here I want to make the combination s of t and this combination, and this is a separate one, so that I can cancel h of f, so that by using this Schwarz inequality, signal power by noise power is equal to, okay, signal power by noise power is equal to, here we can written as integral minus infinity to infinity s of f e power j 2 pi f tb modulus square into df integral minus infinity to infinity modulus h of f square df by n naught by 2 integral minus infinity to infinity modulus h of f square into df, right? This component and this component will be cancelled. Therefore, signal power by noise power is equal to 2 by n naught, okay, integral minus infinity to infinity modulus s of f e power j 2 pi f tb whole square into df, right? We know that the simple equation, any signal in modulus of j theta is equal to 1, right? We know that. So here signal power by noise power is equal to 2 by n naught integral minus infinity to infinity s of f whole square df, right? Now this s of f is a signal, okay, integral minus infinity to infinity modulus, okay, area under the square of Fourier transform is the energy signal. So this is called as energy signal. So see here, this is a finite duration signal. For finite duration signal is always a energy signal, right? This is always a energy signal. So therefore signal power by noise power is equal to 2 by n naught, because of energy signal, this is energy signal, 2 es by n naught, okay. It is very important for the competitive examination as well as GATE, okay. Now this is possible only when, that is here, see, this is possible only when f1 of t is equal to f2 of t complex conjugative of this one, right? Similarly here also it is possible only when, right, this is possible only when here h of f is equal to modulus s of f e power j 2 pi f tb complex conjugative, right? This can be written as h of f is equal to s complex conjugative f into e power, because of complex conjugate becomes j 2 pi f tb. Okay, now we know the h of f. So by using inverse Fourier transform, h of t is equal to s inverse Fourier transform, h of t is equal to integral minus infinity to infinity h of f e power j 2 pi f t dt, right? H of t is equal to integral minus infinity to infinity s, here s of f, okay, e power minus j 2 pi f tb into e power j 2 pi f t s. This is df, right? So this can be written as, please remember this equation, this can be written as, here this can be written as so once again I am writing same equation here, h of t minus infinity to infinity s of f e power j 2 pi f tb e power j 2 pi f t into df, right? So same equation I am written here. So this can be written as h of t is equal to minus infinity to infinity s of f, here I am taking minus j 2 pi common, here 2 pi f, this can be written as tb minus t into df, right? So here this can be written as h of t is equal to minus infinity to infinity s of this can be written as s of f e power j 2 pi f, sir, no, tb minus t complex conjugate. Yes, we can written as like this. So if you observe this one, this equation is simply, for example, s of t Fourier transform equation is s of f e power j 2 pi f t df. It is look like as same as s of t, right? So but here t, instead of t here we are getting tb minus t. So this can be written as h of t is equal to s of tb minus t complex conjugate, right? This is the filter, whatever the filter I am used, that is generated filter is this one. Okay, I hope you will clear the concept of matched filter. Now for example we can see the one example, right? Bit 1, we are representing bit 1 is 0 to tb 5 volts, this is our bit 1, right? This is our bit 1, this is called as s of t, right? To find out the filter equation h of t filter, here I want to find the filter h of t. So filter is equal to, here this is my question, okay, I am solving this question. Question is, design the filter which satisfy h of t is equal to s star Tb minus T. Here I am going to design a filter which satisfies this equation. This is my filter, right? So see here, this to perform this operation, first this is our signal S of t. This signal will be time reversal, that is S of minus t by putting t is equal to minus t. After performing this one, here the time shifting, so that is S of Tb minus t, right, by making S of, okay, by making S of, okay, wherever the t, just I am putting t minus Tb, that is by putting t is equal to t minus Tb, right. So by here, by putting complex conjugative, here it is same as S of Tb minus t, right. So here, see here, this is my input given signal. This signal, first we have to perform time reversal operation. So this is my input signal S of t 0 to Tb 5 volts. This is my S of t. Now S of minus t means time reversal operation. This entire one is shifted negative side, right? Mirror image of this one, that is minus Tb 0 5 volts. This can be written as S of minus t, right? After performing this one, this is shifted towards t is equal to Tb, means positive side. So this can be shifted towards positive side with the Tb duration. The signal is same. This one is shifted towards positive side. So this 0 is going towards the Tb and this Tb is going towards the 0. The voltage is same. So this one, this S of t is changed as S of minus of t minus Tb. Yes or no? This is my signal. Okay. Now if you observe here, this signal and this signal, this both the signal, just I am putting complex conjugative of this one. Right. If this both the signals are same, that's why it is called as matched filter. Matched filter. Now here I want to find the output of the matched filter, that is y of t. Y of t is equal to S of t convolved with h of t, right. S of t signal is this one, Tb 0 S, this is 5 volts, is convolved with h of t is also same signal 0 Tb 5 volts. The convolution of a rectangular signal, we know that that is a triangular signal. That is simple signal operation. Here the value is 0. Here the time period Tb plus Tb, it becomes 2 Tb. The maximum amplitude, that is called energy signal, right. This is the matched filter output y of t. I hope today concept is, the main concept is, please remember, signal power by noise power is equal to 2 Es by n naught. This is one important concept. Another important concept, the filter h of t is equal to S Tb minus t complex conjugative. These two are the important. By using this one only, we can calculate probability error of digital communication system. By using this one only, we can calculate probability error of digital communication system, means the probability error of ASK, PSK, FSK, like. Okay. Now today your assignment is design matched filter. Matched filter. Okay, it is very, very, very important for JNTU exam. Thank you.